key topics we have to look at has to do with predicates, quantifiers, universal quantification, existential quantification, which are the two forms of quantifiers. And then we look at restricted domains. Then we also have to look at what we refer to as logical equivalence. Then we can also look at some translation of sentences to logical expression, and from logical expression to English sentences, right? And then we also have to understand applications of predicate logic as well. So at the end of this session 4, I expect you to have a fair basic understanding of predicate logic, understand preconditions and postconditions. You need to be able to differentiate between existential quantifiers and the universal quantifiers. And also, I want you to be able to know how counterexamples can be used to determine the validity of statements. And then lastly, we should be able to translate English sentence to logical expression. And then, of course, we need to know some applications of predicate logic as well. That's okay. 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 So the recommended textbook, as usual, I'll put it at Sakai for you all to have access to it. Okay. So what is our introduction? We need to be able to know that propositional logic, as we discussed last week, are probably inadequate when you want to express a variety of statements or sentences. But when it comes to dealing with things like I want to find out whether this class, excluding myself, you are about 130. I want to find out whether all the 130 students are punctual in terms of probably muting their mics, and then if there's any assignments on the table, they are doing it accordingly and stuff, right? So I can not use propositional logic to be able to express a variety of students in terms of their punctuality or punctual level, but I can be able to express if a particular student, so maybe randomly I can mention someone's name, maybe AB, is AB punctual or not, right? Looking at the fact that, okay, AB's mic is muted, so I can say that AB is punctual, all right? But if I only look at all the entirety of the class, then I'm going to have an issue. And that is where the predicate logic comes in. So the predicate logic now comes in when you want to be able to have a wide range of statements. And that's the key thing. So some examples I want to be able to give is what I've stated. Every student of University of Ghana is punctual. In this case, every student reading 105, which is a maths for IT professional, is punctual because currently no one is actually unmuted. So I can assume that you're punctual. But based on the propositional logic, we cannot conclude without two statements. We can only do that when we only have one particular statement on the table, like Kwame is punctual and so forth. So predicate logic, as I said, is helpful when you're dealing with every, all, right, etc. Those kind of more than one stuff. So what then is a predicate logic? It's an extension of the propositional logic that permits concisely reasoning about whole classes of entities or everyone on board or all entities on board. That's the main thing. So for example, x is strictly greater than 1, x plus y is equal to 10, x plus y equals to z, right? So this particular statement, we cannot be able to determine the validity in terms of it being true or false unless we know, for example, in this first case, we know the exact value of x. If x is, let's say, 0, and we say 0 is greater than 1, that's a false statement. If let's say x is 1 and then y is 6, 1 plus 6 is giving us 7, and 7 is not equal to 10, so that's also a false statement. If this guy is 0, y is also 0, z is 0, 0 plus 0 is equal to 0. So at the end, we can say that that statement will be true. So such statements are neither true or false when the values of the variables are not specified or they are unknown. A predicate is part of a statement which asserts something about the subject and a consideration. So let's look at an example to differentiate between the subject and then the proposition. So x is greater than, the predicate. X is greater than 3. We can say that P denotes the predicate is greater than 3. So we can say that the predicate is greater than 3. And of course, the subject should be the x, right? So in that case, the above statement can be written as P of x, where we can say that the x is the subject that is expected to vary in terms of changing values. Giving a value to x, P of x becomes a proposition. Again, the statement P of X can also be said as the value of the propositional function P at a given value of X. So this is a typical example. The propositional function will be Q of XY. So assuming X is 1, Y is also 1, then I'm going to have 1 equals to 1 plus 3, which is a false statement. The same applies to A, X, Y, Z. If I know the values of X, Y, and Z, probably X is 1, Y is 1, Z is also 1, then I'm going to have the left hand side giving me the 2, the right hand side giving me a 1. Hence, the propositional function A, X, Y, Z is a false statement. That's it, because the values of X and Y are known. Notwithstanding that we can also have X to be 0, Y is 1, Z is 1. That should be a true statement, okay? So that's the main key thing about predicate logic. Another key example in terms of trying to understand a predicate has to do with this. So the proposition, the cat is sleeping, right? We can assess that statement to be true, or we can assess it to be false, right? The cat is sleeping. So if assuming the cat is with us, I can know that the cat is actually sleeping. It's a true statement. If the cat is not sleeping and the cat is walking around, then we can say that it's a false statement. So it has two parts. The cat denote the subject, right? The object or the entity that the sentence is all about. And then is sleeping denotes a predicate, which basically is a property that the subject can have. Okay. So you can try this. Computer X is under attack by an intruder. This one you don't need a switch here to let me know that computer X is the subject is under attack by intruder is the predicate. Okay. So more examples of predicates. These are minor trivial stuff, right? So P of X denotes X is really greater than 3. We want it to state the true values of P of X equals to 4, P of X equals to 2. So if you look at it very well, once you know X is 4, you made a substitution here that is going to give us 4 is really greater than 3. And 4 is greater than 3. So in that case, this propositional function X equals to 4 is true. Then when it comes here, P of X equals to 2, 2 is not greater than 3. Hence, this propositional function P of X equals to 2 is a false statement. All right. So we come here and then we want to be able to look at AX denotes computer X is an attack by an intruder. Suppose that the computers on campus only CS2 and MATS1 are currently under attack by the intruders, right? What are the true values of ACS1, ACS2, and MATS1? Maybe let's try it. We need some 15 seconds and we look at the answers together. We move on. Right? This one is look and see. So 15 seconds. Okay. Okay, so with that said, you should be able to know that since we are being told specifically that computer X is under attack by intruder, okay, and we know that it's only CS2 and MAT1 that are currently under attack. If the question is ACS1 under attack? That's a false statement because it's not part of the list under attack. Is ACS2 under attack? Yes, that's a true statement. And lastly, is AMAT1 under attack? Yes, that's also a true statement. So that's very interesting, and I'm sure each and every one of you had it right. All right, these are trivial stuff. So we want to move on to something that was shaking you small, right? Still trying to welcome you. Let's kill XY denotes the statement X equals Y plus 3. What are the true values of the propositions kill 1, 2, and kill 3, 0? Yeah, this one too, I'll give you some 15 seconds. Give it a try. And quickly, if one is done, you can raise your hand and tell me the answer, and you move on. Okay. All right, into Enoch, please go ahead.
Okay, so kill of 1, 2 is a false statement. Kill of 3, 0 is a true statement.
Awesome. Awesome. Right. And that's those of you that understand it. Here, kill xy, kill 1, 2 means that x is 1, y is 2. So that's going to give me 1 to be equal to 2 plus 3. And if you check the left-hand side is 1, the right-hand side 2 plus 3 is giving us 5. And they're not the same. So that's why K of 1, 2 is a false statement. Then lastly, if you check K 3, 0, it means that x is 3, y is 0. So the left-hand side, we're going to have x here to be 3. The right-hand side, I'm going to have 0 plus 3. That's going to give me 3. So at the end, I can see left-hand side is 3, right-hand side is 3. Hence, K 3, 0 is true. All right, so let's look at predicates in computer programs, okay? Now, if x is truly greater than 0, then we can say that x is defined as x plus 1. In other words, then we can say that x plus 1 is assigned to x. So this guy is an assignment statement. Another way in terms of mathematics definition is defined as, okay? So in this case, if x is truly greater than 0, in other words, x is positive, right? We know this from what we learned previous sessions. Then we can say that whatever value of x you are having, add 1 to it, and then now assign it to replace the initial value of x. So if initially x was 0, then now we have x to be 1, then I'm going to have 1 plus 1, which will give me 2. So in that case, I'm now going to assign this to the x. In that case, now x will no longer be 0, but x will now be 2 initially, right? Again, if the value of x is, let's say, -1, -1 is not greater than 0. Okay, in other words, -1 is less than 0. So if that is the case, then we need to be able to understand the fact that we cannot come to the then statement. So in that case, the value of x will still be what was initially there. That's it. Now here, p of x is truly greater than 0. Upon taking the value of x, the true value of it is obtained, and a decision of whether to execute the second part, which is x plus 1 is assigned to x, is made or not. Okay. Computer program statements that describe the valid input are what we refer to as the preconditions. And likewise, those that describe the valid output are what we refer to as the post conditions. Okay. So basically, preconditions and post conditions can be represented as predicates to verify the correctness of a given program. So let's consider this particular set of program statements, right? So we're going to have x is assigned to the variable called term, and we're going to have y is assigned to the variable called x. And lastly, we can now have the term assigned to the variable y. So the question on the table is this. Here, the predicate for the precondition is p of xy, whereby we can have the precondition as the valid input, as we explained earlier on for the particular program. X is initially assigned with an A, Y is initially assigned with a B. In the layman's understanding, we can say X is what? A, and then Y is B. And then our main key thing is that for the post condition, we are now saying that, okay, we ended up with what? X being assigned with a B, and then Y being assigned with an A. So there was a swap. So how did we do that? So now let's see how we were able to get it sorted out in terms of how the initial values were X to be A, Y to be B. And then when it hit the output, we had X to be B, Y to be A. So looking at these 3 lines of code, we can now say that initially, we are going to assign X to term. And what is X? X is A. So now term contains an A. Then the next thing is that now, the second line says that we are assigning Y to X. And that Y is the B, which was from the precondition. So in this case, now X no longer contains an A, but rather a B. So that's how the switch of the output of X to become a B happened, because we are assigning the value of B to the variable X. And lastly, we are now going to assign what is in term to the variable Y. And we already know that the value of Y of term initially here was X. And that X, we already know the value to be A. So in this case, we already know when you get here, the term contains the value A. So in this case, if you're assigning term to Y, then what it means is that we are rather assigning what is in term, which is A, to Y. So that's why at the end, we realize that the Y also contains an A. So far, so good. Any question, any concern? Great. Happy you got this. Let's move on.
Sir,
Yes.
please, can you take the example again?
All right, I'll do that. So
Thank you.
we have 3 lines of codes or 3 lines of statements, right? So we're going to have X is assigned to temp, followed by Y is assigned to X, and lastly, temp is assigned to Y. And then we have been given the initial input values or valid input values as X with an initial value of A, Y with an initial value of B. And our main focus is to be able to find the output. In other words, the preconditional values. So for the preconditional values, it means we have to make use of, for the post-conditional values, it means we have to make use of the precondition values. And the precondition values we are given are the valid inputs. X is A, Y is B. So what do? We start with what is here. In here, we know that the X was initially given as A. So at this situation, we are going to assign A to temp. So temp contains what? A. Now, when we come to the second line of statement, we can now have Y assigned to X. And we know Y is what? A B. So we're going to move this guy here. And at the end, we're going to have our B, which means that the X will now contain what we refer to as what? The B. And lastly, we can now come and deal with what? Term assigned to Y. But I already know that term initially contains X, which the X value is an A. So at the end term here is an A. So now I can be able to what? Assign that A to the Y. So in that case, what do I do? From here, I should be able to know for sure that this guy, which is what X is now B, is what I'm seeing here. And lastly, this guy, which is Y, is now assigned with a term, which is what? An A, will now be here. So work is done. So in this case, I have the switch made. B is assigned to X, and then what? A is assigned to Y. That's the main key thing. All right. So I'm sure with this, the understanding is clear.
Yes, please. Thank
All
you.
right. You're welcome. Now we move on to quantifiers. So quantifiers are words which are used to express the extent, right? To which a predicate is true over a range of elements. So we're trying to find the quantity at which, or the extent at which a particular predicate can be true, right? Remember, predicate is dealing with a wide variety, right? So we want to be able to know the extent it can be true. And in that case, we're going to look at 2 main forms. We're going to look at what we refer to as what? The inversal quantification and then the existential quantification, right? So from here, you can see that we are saying that quantification is a way of creating a proposition from a propositional function, which is the same as a predicate, using what we call quantifiers, okay? And then, as I mentioned, there are 2 main types. You have what we refer to as well, the inversal quantification or quantifiers, the existential quantification. Now, the area of logic that basically will deal with predicates and quantifiers is what we refer to as well, the predicate calculus or the predicate logic, right? So we're going to start with the domain, right? The domain of discourse or universe of discourse. We can say that the domain basically is a set of possible values that a variable can assume. And that's a very key thing. The set of possible values that a particular variable can assume is what we refer to as what? The domain. And of course, the inversal quantification of P of X is a statement that P of X for all values of X in the domain. And normally we use this symbol to denote that for all x, or for all, or for every. That's the meaning. Then, for us to be able to know that the investor quantifier is false, then we need to be able to identify a particular value in the domain that makes it what? False. Once we get that, then at the end, we can say that the whole universal quantifier is false. So a typical example is you are expected to mute. Then peradventure someone mistakenly, right, unmute. And then maybe the caveat is that if I hear someone probably disturbing, I'm giving an example, please pay attention here. I'm going to conduct a quiz. So if mysteriously someone from nowhere just on mute, right? And I get to know, then of course, whether you like it or yes, you're all going to what? Take part of the quiz. Although someone has actually been able to make a mess. It's like you chewing peanut, and from nowhere, one of the peanuts is faulty. Sometimes even if you are taking wachi, right? And you realize that there's a stone in one of it, or even curry and beans, you are tempted to throw everything out. And that thing that causes you to be attempted to throw everything out is what we refer to as a counter example. Okay, so an element in the domain for which P of X is false is called what you call the counter example. So the counter example let us know what exactly is false for us to throw everything out. Okay, so that's it for the counter example, right? So the meaning of for x p of x changes when the domain also changes. Okay, so initially the domain was set of integers, and then later the domain now becomes set of positive integers. Then it means that we are not looking at everything from the domain of integers, but rather we are looking at a section or a fraction of it. Okay. So inverse quantification example. So let's take this kind of examples. Let P of X be the statement X plus 1 is really greater than X. The question is, what's the true value of the quantification for all X P of X, where the domain will consist of all real numbers? By now, each and every one of you know what a real number is, right? Basically, a concatenation of rational and irrational number, right? And then we know that rational numbers are numbers which are basically in the form of A over B, where B is not equal to 0. A and B are basically belonging towards the set of integers. And then A should be the numerator and B should be the denominator. These are basic things we already know. And of course, when we're looking at irrational numbers, they are numbers which are not in the form of A over B, the repeating exponents and so, etc. We looked at it. Okay, so now we come inside here, and then our main question on the table is this particular statement true when you are dealing with 4x? So for it to be false, then the secret is that, can I be able to get a particular value of x that will make this statement false? That value of x should come from the set of real numbers. If I should be able to get a particular value of x, that when I add 1 to it, okay, instead of being greater than x, it will rather be less than x, or less than a particular number, then I can say that the statement is false. Now, if you sweep across all the real numbers, no matter what, if I pick less than 0.1 and I add 1 to it, I'm going to get 1.1. And that 1.1 is greater than 0.1, I pick as x. If I pick negative 1, right, and I add 1 to it, I'm going to get 0. And of course, 0 will be greater than negative 1. So any number at all you can think of in the family of real numbers, there is no way you can get a counter example. Hence, this particular statement is true. You good? Now, with this said, can we all try the second and the third examples quickly? So I see Charles hand up. Yeah, Charles, please go ahead. So you try the second one. Okay. Charles.
Good afternoon, sir.
Yeah, good afternoon, Charles.
Yeah, please, sorry, this one, it looks like I've missed a lot because last week I couldn't join, and then today too, the network is not stable for me. The Zoom, it has been connecting and disconnecting, so the whole thing, I'm confused. Can you please help me a little bit?
Sorry, I'm lost. Why are you confused about? Maybe, as I always tell you guys, let me ask, have you guys created a groups, the study groups I
Yeah, we have
mentioned?
a WhatsApp group.
No, no WhatsApp group. The study groups.
Yes, sir.
You have it.
Yes.
Maybe you can
Sir.
share with me and then I can put it on your Sakai. I think I got some complaints that some of you are not joining the classes because you're not seeing the Zoom link. So if you go to Sakai, I've actually placed the Zoom link there at the announcement session.
Yeah, the link is there.
Okay. All right. So not to drag us back, let's move on and then maybe try and catch up. If there is something you don't understand where I am, then I can be able to explain. But from what you are
Please,
saying,
do you have the recorded version of the previous sessions?
your colleagues are having it, so I think they are circulating it on your WhatsApp pages.
Yes.
So please pay attention
Okay.
to your page, right? Maybe what they can do is that if you can share with me, I can actually upload on Sakai so that you can all have access. But I encourage everyone to be on the WhatsApp page, guys. Okay.
Okay. I'll be glad if it could be on Sakai so that we all have access.
Please stop writing on my screen. Those of you doing that, stop it. Okay, so quickly let's come back to where we are. Joshua, please, I see your hand up. You want to try the second part?
Yes, sir. The second one is false.
Okay. So you want to explain why it's false in your opinion?
I think when you choose X to be 3, it will make it false.
Okay. And that X being 3 is what?
Please come again.
X being 3. What name do we give to it?
What name do we give to the X?
Being equal to 3. The example you gave.
You said we should look for integers, right? That will make the statement false. So when you take any number greater than
And I'm
the
asking
2
that
and you put
when
it in.
X is equal to 3, what is the
Mhm.
meaning of the example? Anyone want to do that? Emmanuel, Sherry, Samuel, Ebenezer.
Yeah. Yeah,
It's
sir.
a
It's
counter
a counter
example.
example, please.
Very good. So at least I have people in the class with me. So that's an example of a count. That's what we call the counter
Okay.
example.
Yeah.
Okay. So please, what you just mentioned right now, which indeed the true value, okay, is false because when X is 3, in fact, when X is even 2, right, we can actually not say that that particular statement is true because 2 is not less than itself. 2 is equal to itself. So when X is 2, when X is 3, when X is 4, when X is 5, etc., okay, still in the domain of real numbers, in other words, 2.1, 2.2, right? In other words, 3.7899, they are real numbers. We cannot be able to say that it is actually a true statement. So because of we finding a counter example, we conclude that the whole of the second example or the second part, X is really less than 2, is a false statement. Now, the third one, suppose that P of X is really greater than 0. What is the true value of the quantification for X P of X for the domain of integers? Yes, let me see which hand is up. So, into.
Okay, so when the x values are negative integers, you're going to have the statement to be false.
Okay. Okay, that's fine. Hey, I think I just saw someone with Solomon, right? So let me differentiate and use my full name. Right. Yes. I have my full name too. All right, good. Awesome. So your statement, please, into what was the answer? I didn't get it.
My answer was that when the x values are negative integers, then it will be a false.
So is
It will be false.
the whole question true or false? Because the question was the true
It's
value.
false. It's false.
Yeah, because we can find a counter example, right?
Yes, please.
It's false because we can say that x equals to 0 is a counter example. Are we good? That's the main key thing, right? What's the true value of for x p of x, where p of x is the statement x is straight. Abdallah, please mute. Okay. What is the true value of for x p of x, where and p of x is the statement x is really less than 10, and the domain consists of the positive integers not exceeding 4. Terry, appear.
It is a true statement.
Why?
It's a true statement because it is what it's looking for is positive integers not exceeding 4, and so we have 0, 1, 2, 3. 0, 1, 2, 3, which is less than 10.
Okay. So these are positive integers, right? So if they are not exceeding 3, then we are looking at 0. I'm sorry, 0 is not a positive integer.
Sorry, 1, 2, and 3. Yeah.
Awesome. Awesome. Great. Oh, sorry. What about this? So this basically is a true statement, the first one. Okay. What about the second one? What does the statement for x, n of x mean if n of x is computer x is connected to the network and the domain consists of all computers on campus? I see one Dennis. Dennis, your hand is up.
Well, sir,
Yeah.
please, the statement is true because computer X is part of the whole domain, the computers in the school.
Okay. So the question is, what does the statement for all x, n of x mean? If n of x is computer S is connected to the network, that's the first part of the question. And the domain consists of all computers on on campus. So what does the statement mean? This one is not asking what's the truth value.
The statement is asking whether X is a subset of the whole of the statement, whether computer X is part of the computers on campus.
No. You have to be careful. The question is not asking you to find the true value or the validity. The question is saying, what does the statement for all x, n of x mean? And he has told you what is n of x. Anyone?
Hello, sir, I can hear you.
Yes. So I want someone to try and attempt that question. What does it mean for x, n of x? Yes. Can you raise your hand when you want to call it up? All right, Justice, go ahead.
So please, which means the X is also part of the domain.
So basically, okay, Joshua, I see your hand up.
It's my understanding. I think it means that all the computers on the campus is connected to the network.
You've added some stuff to it.
All computers on the campus are connected to the network.
Okay. Yeah, I'll take it. I'll give it to you. So it means that this means all. So all computers, right, on campus, right, is or are connected to the network. Another way you can say it, remember the 4x, we can use, this means that for all, or we can use every. So you can also say that every computer X, right, on campus is connected to the network. Every means all. Are we good? So that's what the statement means. So this one is not asking you to find a true value. It just asks you to explain the statement. And for x, n of x. Now, what's the true value of for x? X is greater than or equal to x if the domain consists of all real numbers. What is the true value of this statement if the domain consists of all integers? So let's start with any of them. If you want to talk about in terms of real numbers, fine. If you want to talk about in terms of integers, it's fine. So this is where a true value will come in, whether it's true, provided you didn't find any counter example, or it's false, provided you found a counter example. Sherry.
It's false because when you take the x is greater than or equal to x, you take the set of negative. You take the set of negative numbers.
Sherry, hold on. Which one is false? Is it the first one in terms of real numbers, or the second one in terms of integers?
The in terms of real numbers.
Okay, go ahead.
Because if we have -1, we can't have you can have x, which is -1 is greater than or equal to -1, which makes the statement false. If you take the set of negative values.
Okay. Anyone else? If you are looking at what Sherry is saying, if you pick a value, right, you cannot be able to have it greater than itself. But you can see this is greater than or equal to. Be careful. This is x is really greater than x. Yes, anyone else?
I also think it is true statement because of the equal to, greater than or equal. So any value you pick for x, it will be greater than or equal to x for the real numbers.
Okay. Anyone else?
Yes, sir. I also think it's for the real numbers, it's a truth because all means that one of the conditions have to be true for the statement to be true.
Great. All right, so that's it. So if you can see, because we are dealing with the disjunction or, this is x is greater than or equal to x. So for the disjunction, we need one of them to be true. So no matter what it entails, you are always going to get the value, one of them being true. And since one of them is going to be true, we are good to go. We can say that for every real number you pick, we can get it equivalent to the other. And since we cannot find a real number that will be greater than another real number, then we cannot be able to stick to the equality part and conclude that this particular statement is true. The integers too, if you check very well, it is also going to be the same domain and the same family to be true because of the equality there. So, existential quantification. Now, for the existential quantification of P of x, is a proposition. There exists an x in the domain such that P of x. Now, this is denoted with this symbol, there exists or there is. Okay? So, if you can see, this symbol means there exists. The same symbol also will mean there is. Now, similar to the universal quantifier, a domain must always be specified when you are using the existential quantifier with this symbol. And the meaning of there exists x P of x changes Here too, when the domain also changes. So let's look at this table and try and understand what exactly is going on in terms of when the statement should be true and when it should be false. So let's start with the first part. So the inversal quantifier for x p of x. We are saying that it is true when p of x is true for every element of x in the domain under consideration. Again, it is false when there is an x for which p of x is false. So what does it mean? It means that for us to be able to have the inversal quantifier to be false, we need to be able to locate that counterexample, right? That will be able to make the statement false. Then we can draw a conclusion that is false. Now, there exists x p of x. So in this case, there is an x for which p of x is true. So once we're able to find a particular single value of x that can make p of x to be true, then we can say that it is true. Come on, let me see. And it becomes false if you have been able to access all the values and then see that it is false. Are we okay? Just a second, guys. Okay, so that's it for this particular table. For the first part, for inversal quantifier, it is always true with the exception of you finding a counterexample that will make it false. And the vice versa already holds for the existential quantifier. Once you're able to find a particular x that makes p of x true, we can conclude that the whole there exists x is true because I'm looking for at least one of the x to make it true. And the last one is that for the existential quantifier to be false, then it means that I've been able to access every element in the domain to make sure that they are always making it false. I can't single one out to make it true. If I only have one to be true and the rest is even false, then in terms of existential quantifier, it is still true. Because existential quantifier means that I need to find at least one of the x that makes p of x true. So with that said, we can also still now look at examples for existential quantification. So let's see how we go about it. So for example, let p of x denote the statement x is really greater than 3. What is the true value of the quantification? There exists x p of x when the domain consists of all real numbers. So looking at this one is trivia. I'm trying to see how best you can handle it. I see a hand up. Pascal, go ahead. Pascal, hand is down. Yeah, Pascal, go ahead, please.
So this is true.
Okay. Why?
The answer is, there can be a number which is greater than 3.
For example.
4 can be greater than.
Okay, sure. In other words, so you are looking at a real number, you can even have 3.1 is greater than 3, 3.00001 is greater than what 3. So that's a true statement. Once we come across 1, we are good to go to make a decision. Now let's look at the second one. Let K of x denote the statement x plus 1 is assigned to the x. What is the true value of the quantification? There exists x K of x where the domain consists of all real numbers. Can you be able to find a particular value to make this true? Or we draw a conclusion that is false. So I see Sherry. Sherry, your hand is up.
We have values which will make the statement false. So the truth value is false. Because if you put x to be 0, we get 1, which means we can never have a number which will give you exactly the value of x we want.
Your explanation is not really clear, so I'll not give it to you, although your answer is correct. Joshua, please let me hear from you.
Since you are looking at raw numbers, let's take 1.1. So 1.1 is equal to 1.1 plus 1. That will give us 2.1. So with that, we can conclude that it's false.
Okay. Okay, let me hear from another person again quickly. Benjamin.
Okay, so for every value you use as x, it will make the equation false because both sides will not be equal.
Yeah. So for every value, no matter what, remember, for us to be able to say that the existential quantifier is false, then it means that we have been able to assess all the possible values in the domain, and we can draw a conclusion. So no matter what it entails, this guy will be false because there is no way you can actually be able to get at least a single value that will make that particular statement true. So for every possible value in the domain of real numbers, you always get this thing to be false. Okay? Now, what about this? When the domain is empty, what happens? Yes, anyone? When the domain is empty, what happens to the universal quantification and existential quantification?
I can say it's neither true nor false.
Are you sure?
That is my opinion, though.
Okay, so without wasting time and making it a debatable stuff, let's go straight to the answer. It's a very interesting thing, though, but pay attention here. For x, p of x is always true. And lastly, there exists x, p of x is always false. That's what makes math very interesting and very nice to do with. So why is it the case? Let's look at it in this way. So what do we know? We know that for x, p of x is always true, meaning that we can only make for x, p of x false, provided we have a counterexample. And since the domain is empty, we cannot find a counterexample inside. Hence, we draw a conclusion that for x, p of x is always true. Because we need a counterexample from the domain to make it false. And this is the case the domain is empty. So that makes for x, p of x always true, because we can't get a counterexample in the domain. Now let's look at the second part. There exists x, p of x is always false. For existential quantification to be true, in other words, that there exists x to be true, we need to be able to find at least one of the x from the domain. And this is the case the domain is empty. So where do you find that particular x to even test to make p of x true or false? So in that case, since we cannot find any suitable candidate of x in the domain, we draw a conclusion that this existential quantification is always false. Very interesting, right? Any question on this? Awesome. Let's look at some exercise on that. You're expected to find a counterexample, if possible, to this universally quantifiable statement, where the domain for all variables consists of all integers. So these are just three of them. Quickly put your heads together, then after we discuss it. So please work on this for just some few 5 minutes, and then I'll join you shortly.